first reaction we'll be talking about today is the Grignard reaction. This reaction was discovered in 1900 by Victor Girgnard. He won a Nobel Prize for his discovery in 1912. This reaction is important in synthesis because it combines basic organic compounds into more complex ones. Grignard reactions are very useful as they provide ways to synthesize carbon-to-carbon bonds, alcohols, carboxylic acids, and more. The formation of a carbon-carbon bond is critical in scientific and industrial contexts. As pictured, tamoxifen can be created using a Grignard reaction, which is used for the treatment of breast cancer.
Before you can perform a Grignard reaction, you have to prepare the desired reagent. This can be done by reacting the desired carbon chain bonded to a halide with magnesium metal in an ether solvent.
There is initially a partial negative charge on the bromine. This allows the magnesium to easily insert itself between the bromine and the carbon. Once the magnesium has been inserted, there is a partial positive on the magnesium-bromine complex and a partial negative charge on the carbon it is bonded to.
Grignard reagents are very strong bases and react readily with compounds that contain a hydrogen that is bonded to an electronegative atom. The carbon directly bonded to the magnesium metal in the Grignard reagent behaves as if it is a partial negative charge. This allows the carbon to act as a nucleophile in addition reactions. The partial negative charge on the carbon attacks the carbon of the carbonyl. The electrons joining this carbon and the oxygen move onto the oxygen, giving it a negative charge. The original carbonyl carbon is now bonded to an oxygen. The original methyl group, and now also our Grignard, we have made a carbon-carbon bond. The oxygen now takes a hydrogen from the acid to form an alcohol. Here's a synthesis problem using a Grignard reaction. Pause this video and try to figure out the steps needed to produce this product.
The steps necessary to produce the desired product are to first do a non-Markovnic hydration by doing a hydroboration oxidation with BH3, THF, and a H2O2 and NaOH solvent. Next, we must oxidize with PCC and DCM to produce the aldehyde. Finally, we will add the Grignard reagent with water to create the desired product.
Wittig reactions are another method for making carbon-carbon bonds. In a Wittig reaction, a phosphorus ylide is reacted with an aldehyde or ketone to form a carbon-carbon double bond. George Wittig and Herbert C. Brown discovered the reaction in 1954 and won the Nobel Prize for their work in 1979 for their development of the use of boron and phosphorus-containing compounds respectively into import reagents in organic synthesis.
Much like the Grignard reaction, the Wittig reaction requires that the reagent be prepared before the reaction can be carried out. To prepare a Wittig reagent, an organic halide is reacted with triphenylphosphine. The preparation consists of two steps. The first is an SN2 reaction, and the second is an acid-base reaction. These reactions produce the phosphorus ylide, which then reacts with the carbonyl to form the desired product.
The initial step of the Wittig reaction involves a nucleophilic attack that results in a four-membered ring. In the second step, double bonds and two alkenes are formed. One consists of an oxygen double bonded to the triphenylphosphine and the carbon of the original carbonyl double bonded to the ylide.
Please take a few moments and pause the video to see if you can determine the original reactant and the steps necessary to produce the desired product. In order to create the desired product, the original reagent butanol is needed. First, the alcohol group must be oxidized to form the aldehyde so the Wittig reaction can occur. PCC and DCM were used to create the aldehyde, and the Wittig reagent was added. With the Wittig reagent, we now obtain 3-ethyl-3-heptene, which, when used with a halohydronation with Cl2 and H2O, will create the desired product.